All right, this is 11.6. This is, let's say, planes in 3D space. So just to begin with, let's make sure it's clear to us exactly what a plane is. Right? So a plane, this is going to be a somewhat loose definition until we have an official definition, and then we'll be good. But a plane is a flat surface extending forever in all directions. Well, I say in all directions, but extending for, I'll just say extending forever because it doesn't extend up and down, of course. So we have 3 planes already. We know 3. We know the XY plane, the XZ plane, and the YZ plane. All right, again, in order, we drew these back the very first day. The XY plane looks like this. It's the tabletop at the beginning. The XZ plane looks like this. And the YZ plane is like the screen, if you like, and the x-axis sticks out from it. And these have equations, right? We can actually, even though we never wrote down equations of these before, right, so we can intuit the equations. In other words, intuitively we can figure out what they might be, right? So for the first one, the xy plane, we can see that in this one the height is always 0, and that's the z value. So we could suggest maybe that's z equals 0. The xz plane, right, this one right here, intuitively we can say, well, y is always 0 there. So it seems reasonable that that's the equation. And the yz plane, you can probably guess x equals 0, this one right here. And you'd be right. There's no forward, there's no back, there's no x direction. But there are lots of other planes, right, that maybe go on angles. And let's say, but other planes exist. Right, like you could draw one, for example. You could say, well, here's XYZ space. And maybe there's a plane that like sits at an angle like this. Maybe the z-axis pokes through it. And it goes forever and ever in all directions. Right, we could shade that in if it helps. I'm not generally going to shade planes a lot, but let's shade that one in. And I'm only drawing a rectangle, but it does go forever in all directions. You could think of it as like a tilted XY plane, for example. What would be its equation? What would be the equation, let's say, of something like this? So what we'll do is we'll call this definition / formula. And so what we'll do here is we'll sort of talk about how to construct the equation of an arbitrary plane. And that'll lead us to an official formula, and then we get to define a plane that way. Right? So there are a variety of ways that you could describe a plane hanging in space. You could, for example, give 3 points and maybe suggest that a plane must contain 3 points. But there's sort of an interesting way which will be useful to us. So what we'll do is we'll start with a point. So it's a bit like with a line, interestingly. We're going to start with a point and a vector. But that vector will have a special name. It'll be called the normal vector. Now, the word normal in mathematics is often also used to mean perpendicular. The terms are interchangeable in some contexts. So the normal vector will be n bar. And so visually, just like with a line, you can picture the P, the point P, and the normal vector. Think of this in 3 dimensions, just being attached to it. And if you're having trouble visualizing this, you can pick up a pencil, for example, and you can imagine that the eraser is the point and the pencil is the vector. And then that could be anywhere in space. So then you might say, like, well, how does this describe a plane? So it turns out it's fairly easy. What we'll do is we'll attach the plane, right? Imagine a flat surface. I'm going to say a flat plane. Let's say through P, which is perpendicular to N. So I'll say which is perpendicular to N. So visually, you can picture something like this. Here's your P, here's your N, and then I'm going to picture a plane. I'll do it in a different color. Let's say blue, which would be, you can picture this here, which is perpendicular right here in all possible ways. So again, if you have a pencil handy and you hold it up and the eraser is the point and the pencil is the vector, you could take a sheet of paper, you could hold it where the eraser is and make sure that it's perpendicular, that the normal vector is jutting out of it perpendicular. There's only one way to create such a plane. That's our plane. So this is great visually, right? You could draw lots of little pictures with planes and vectors, right? Let me scratch a few on the side. You could be like, there's a vector and a point and a plane. There's a vector and a point and a plane. There's a vector and a point and a plane, and so on. But it doesn't really necessarily immediately tell us what the equation would be. So what's the equation of such a plane? So what we'll do is let's develop the equation. We'll go back to a point. We'll start with a point and a vector. The point will have coordinates. The vector will have components. And we'll write down what it would mean for another point to be on this plane. So let's do that on the left. So let's do this. Let's draw a pretty detailed picture where we can decorate the picture and put some other stuff on it. We'll draw a plane right here. That will be our plane. We'll draw a normal vector, perpendicular, in fact, right there. And we'll label things a bit. So this N will be AI plus BJ plus CK, the point P. Let me do this. Let me draw a little arrow pointing to it. That is our P, X0, Y0, Z0. And then what we'll do is we'll take another point, this point right here. This will be the point, let's say Q equals X, Y, Z. We're going to ask a very simple question. What would it mean for Q to be on the plane? Or what do we, let's say, get out of knowing that Q is on the plane? So if we look back at the picture, this is what I'll do. I'll draw another line. I'll draw a line. Really, I'll draw the vector from P to Q. That vector. Now, if you think about it, if Q is on the plane, then when I draw the vector PQ, the green vector, that will make a right angle with the vector N. Right? So this is PQ right there. So what happens is, for Q to be, so this is question and answer. So the answer is, if Q is on the plane, then the vector PQ, let's say, makes a 90-degree angle with the vector N. And if you look at the picture again, you can see that that's true. You say like, okay, well, 90-degree angles means they're perpendicular. What do we know about perpendicular? We know that if two vectors are perpendicular, dot product 0. Right? So what this means is that N dot PQ must be 0. So then we say, what does this mean? Well, what's the dot product? What's PQ? So we go, okay, well, N, we know that. That's AI plus BJ plus CK. That gets dotted. Okay, what's PQ? We do PQ by taking Q minus P. That's X minus X0I plus Y minus Y0J. This is all PQ that I'm writing down now. Z minus Z0K. That must all be 0 then. So if we dot these out, we get a x minus x0 plus b y minus y0 plus c minus z0 equals 0. So this is the equation. Notice this isn't a vector anymore because we took the dot product. This is a regular equation, right? So this is the equation with point P. That's x0, y0, z0. And normal vector. Again, think if you like perpendicular vector. The official term is the normal vector, but if it helps you remember for now, think perpendicular vector. N equals AI plus BJ plus CK. That is it, right? And that's a nice equation. You can plug things in, check if they're on the plane, etc., etc. So let me do two examples. I'll do one where everything's just given. We'll just plug some stuff in. Then I'll do one that's a little bit more tricky. And then what we need to do is we need to talk about how to draw these things. So next thing, just some simple examples. So a really simple example, we could say the plane containing the point, say 1, -2, 5, with normal vector, say n equals 4i plus 6j minus 3k. This has equation. And so literally we just plug everything. We take the coefficients of the components of the vector, those become the coefficients. So 4 times x minus 1, that minus 1 is from the point, plus 6, y minus a minus 2, plus -3, z minus 5 equals 0. Now, that can be simplified, right? Formally speaking, that's it. You're done. You've got the equation. But it's worth simplifying for two reasons, as we'll see. So if we simplify this, we get 4x minus 4 plus 6y, it's plus 2, so plus 12 minus 3z plus 15 equals 0. 4x plus 6y minus 3z equals, so we have -4 plus 12 plus 15. So we have 27 minus 4 is 23. Subtract that. We get this. So this is sort of the simplified version. This simplified version is particularly nice because if you want to know, so two things. Thing one is, this is really nice because if you want to know if a point is on the plane, just plug it in. Right? You could say, for example, is 1, 1, 1 on the plane. And you go, well, 4 times 1 plus 6 times 1 minus 3 times 1 is definitely not -23, so no. That's the first thing, right? And that's easy, makes it really easy when it's simplified. The other thing is just a note to point out is when you rewrite it like this, if you go from, let me point this out with some arrows, if you go from this original form up here down to this form, you don't really see what the original point was. Like, it doesn't matter, that's not a bad thing, right? But you don't see what the original point was when you constructed it. Like the 1, -2, 5 is lost in there. However, the 4, 6, -3, the normal vector, is still there, right? So just observe the coefficients of x, y, z came from n. So that can help you see what the normal vector is. So, nice simple example. Now let me do one more example, and before I do it, I'm going to clear the screen off, and I'm going to do an example that comes back to a comment that was briefly made at the beginning was, 3 points make a plane, as long as they're not all together in a line. So if you have 3 points, how do you get the equation of that plane? And so let me work through that. Let me clear the screen off and do that example. So we'll say, for example, suppose a plane contains the points, say 1, 2, 1, 5, 6, 3, and 8, 2, 10. Find the equation of the plane. So keep in mind what we need to do to find the equation of a plane. We need a point and we need a normal vector, a perpendicular vector. One of those is easy. We have 3 points. So we need a point and we need an n. Right? So the point is easy. We have 3. So it turns out we'll be able to use any of these. Any of them, all 3 of them are on the plane. Doesn't matter which one we use. How do we find an n? So here's the deal. Let me label these points. Let me call the first one P, second one Q, third one R. So let me draw 3 points. I'm not going to plot these in a plane. I'm not going to plot these rather on an axis, just because I don't need that. I just want you to see something. All right, so we've got a P, we've got a Q, we've got an R. So what we'll do is this. I'm going to construct 2 vectors. I'm going to construct PR, which would be this one, and PQ. I did those in reverse order, that's right. PQ and PR. And now, keep in mind, these 3 black points, these are in our plane, the plane that we're trying to find the equation of. So imagine there's a plane that contains all of this stuff so far. So then we say to ourselves, okay, I need a vector which is perpendicular to the plane. If it's perpendicular to the plane, then it's perpendicular to PQ and to PR. How do I get that? That's the cross product. Remember, the number one use of the cross product is when you cross product 2 vectors, you get something perpendicular to both. So what we do is we take these 2 vectors that we just constructed, PQ down there, PR right there. We cross those, and when we do that, by the right-hand rule, we get something that points up, or maybe down. It doesn't really matter. The point is it's perpendicular. Right, so we do PQ cross PR, and this is our n. Now, so we'll do this in a second, but notice that you might say, like, well, what if I did, instead of PQ, PR, I did, say, QP and QR, or RP and RQ, and cross those? That would be fine, not a problem. You have choices. I'm just going with P because it's the lowest letter of the alphabet, but it doesn't really matter as long as you construct the vectors and cross them. Right? This is what we'll do. Let's write all these down. So remember, for PQ, I do Q minus P. So I get 4i, that's 5 minus 1, 6 minus 2 is 4, 3 minus 1 is 2. That's K. For PR, I do R minus P. So 8 minus 1 is 7, 2 minus 2 is 0, and 10 minus 1 is 9. Then we cross these. So I'm going to do these little determinants in my head without writing anything down. So remember, for the I component, I do 4 times 9 minus 0 times 2. So that's 4 9s are 36. For the J component, we do 4 times 9, 36 minus 14. So that's 22. For the K, we do 4 times 0 minus 7 times 4, which is negative 28. This is our n. So thus we know equation is then 36. Remember, I take the coefficients from the components from n, those become the coefficients, and I'm going to use P from a point because we had 3. I'm going to use the first one. So 22 1 minus 2, and then minus 28 z minus 1, and that's equal to 0. And the little note that I'll end on, I'm not going to simplify this for now, but the note that I'll end on is we could have done lots of the following. You could have done n being, say, RP cross RQ. You could have done n is QP cross QR. We could have used, we use P up in here. could use Q or R. Now, you might get an equation that looks different, right? The numbers might be a little bit different, but if you multiplied everything out and simplified it, the results are all equivalent. So we see that a lot. We see things that might look a little different, but they'll be the same if you arrange the equations appropriately. So I wanted to do this example specifically to make this ongoing point of all of this, is we always need an n. Right? If it's not given, you have to find it one way or the other. So in this case, it took a cross product to do it. So take a look at this, make sure it makes sense. So what we're going to do next is we're going to talk a little bit about sketching planes, because when we talk about equations of lines, that wasn't so important. We're not drawing a lot of lines. However, we will be drawing a lot of planes. So because we'll be using planes to draw objects as we go. So next thing I want to do is look at some different types of equations of planes and just draw some examples of what these look like. So let me clear the screen off and break it down. They're basically going to fall into three categories. We'll say 3 sketching planes. Now, just like with spheres at the beginning, the important thing is that you draw things that make sense to you. And so there can be planes, for what it's worth, which are very difficult to draw. They're at weird angles, they're hard to visualize, etc. So don't think that you should emerge from this knowing how to draw every single plane you will ever accomplish. You just need to have sort of a limited vocabulary so that we can discuss things and draw things, and I can describe objects to you and everything's good. So don't panic too much if some of them are challenging. Just work on lots of different examples and you'll be good. So what we'll do is we'll look at 3 types. And there are some subtypes. It sounds awfully threatening, but it isn't. So the first 3 I want to list is I want to list the ones that are somewhat familiar to you. So we know, for example, what x equals 0, y equals 0, and z equals 0 look like. Those are the original 3 coordinate planes. So let's look at some things that are like that. So let's call these, I'll call these the easiest. I'll just do 3 examples. Say z equals 2. You can probably guess what that's going to look like, right? Z is 2, that's a height of 2. X and Y could be anything. So just a little note here. This does have the original form. In other words, this really is 0x plus 0y plus 1z equals 2. Right? This is an honest-to-goodness equation of a plane. Right? It does have the correct form. But in any case, it's just written a little differently. So this is easy to see. It's at a height of 2. There's the z-axis. There's the x-axis. And there's the y-axis. And this is at a height of 2 right there. So easy to draw. It's parallel to the xy plane. Next one is something like, say, y equals 3. The y-axis is to the right. So this one will go to the right. Be 3 units over. Again, this just doesn't need to be perfect, just reasonable. This is out at 3. And something next would be, say, x equals negative 1. X is forward and backwards, so this is backwards 1. This is probably the trickiest to draw. This isn't negative 1. Again, you don't need to have perfect pictures. I'm only drawing partial axes here. You can fill in more axes, but it can be a little overwhelming. So only fill these in if it helps with your picture. Don't think that everything needs to be gorgeous. Right? So these are sort of the 3 basic parallel types, if you like. They're parallel to the planes that you're familiar with. They're the easiest to draw. Keep in mind they go on and on forever. Now, notice as we do this, right, it's important to keep in mind, we saw this with our first example, is all planes do have the form, when you rewrite them, ax plus by plus cz equals d. Right? You can always take that original form, the a times x minus x0, etc., and sort of shuffle things together and rewrite it. So all of these, you see like this second one, this really looks like 0x plus 1y plus 0z equals 3. You don't need to rewrite it that way, but it can help to remember that it is in the correct formula. This is 1x plus 0y plus 0z equals -1. All right, so B. I'm going to call these the triangle planes. This is a weird description, but it's going to help us remember what we're actually going to draw. So consider, I'll give you an example, something like 2x plus 3y plus 4z equals, say, 12. What I'm going to do in this is I'm going to find all the intercepts. And so planes that have the form like this, ax plus by plus cz equals d, where none of the a and the b and the c, none of the coefficients are 0. Right? Those are these little triangle planes, I'm calling them. Right? So what we'll do is we'll find the intercepts. So the x-intercept is where it's on the x-axis, it's where y and z equals 0. So that's 2x plus 3 times 0 plus 4 times 0 equals 12. So that's x equals 6. The y-intercept is where x and z are 0. So you don't need to write these down. You can actually just look at the equation and see what it would be, but I'll be really pedantic this time and write everything in. So here we got y is 4. And the z-intercept, this is where x and y are 0. This is 2 times 0 plus 3 times 0 plus 4 times z equals 12. So z equals 3. So what I'll do is this. I'll draw the axes. And then I'll draw some tick marks here to give it a sense of scale, because that can help a little bit here. And if we plot these points, I need to go further in my x. Let me tidy this up a bit. This is my x equals 6. This is y equals 4. This is z. Oh, sorry. This is y equals 4. And z equals 3. So the plane goes through these 3 points. So what I'm going to do is I'm going to draw a triangle. Now, this triangle is not the whole plane. This triangle is just a piece of the plane. The plane extends out from this triangle in all directions. It's actually fairly hard to visualize. But usually drawing this triangle is good enough, right? So generally we have this overall consensus that what we've drawn is just a piece of the plane in all cases. But if you wanted to draw a bigger piece, I'll do it on this picture, but you don't need to. You can imagine that you've got this giant plane that cuts through the axes at a weird angle, and those 3 points are the intercepts where it hits the plane, where it hits the axes. So that's what's going on here. But if you draw a rectangle, it could be a bit confusing. Drawing a triangle is usually a bit easier. So typically, when we have this situation where none of the coefficients up here are 0, the solution is to find the x-intercepts and draw a triangle. And that's usually enough to wrap your head around what's going on. So if you look at what's taken care of here, what's done is we've taken care of the cases where you just have an x, y, or z, the first 3, and we've taken care of the case where you have all x's and y's and z's. So the only case that's missing, or let me just be really, really clear about this before we go further. This is like the case where a and b are 0. This was the case where a and c are 0. And this was the case where b and c are 0. This is the case where none of them are 0. So the last case is when one of them is equal to 0. So what I'll do is I'll clear the screen off, and there are 3 of those cases. They're all very, very similar, so it shouldn't feel overwhelming, but I'll do an example of each of those. So, see, let's say the case where one of A, B, and C are 0. So take a look. We'll do an easy example first. 2x plus 3y equals 6. Now, a little note here. Arguably, you could, if I had given this to you before the course started, you might just think this is a line. So context matters, right? The fact that this is a plane is premised on the fact that you know we're in Calc 3 and we're talking about 3-dimensional objects. So context matters. In other words, if I just said to you, sketch 2x plus 3y equals 6, and you drew a plane and you drew a line, you'd be right. But if I said to you, sketch the plane 2x plus 3y equals 6, then you know, right? So in 3D, this is a plane. So let's think of how we want to do this, right? It's an equation, right? Again, this is really the equation 2x plus 3y plus 0z equals 6, right? That's really what's going on here. But in this equation, there is no z, right, the way it's given. And I mentioned this in the section on lines, but equations are restrictions. So since there's no z in the equation, there are no restrictions on z. So z could be anything. So what we're going to do is this, and we'll do a similar thing for the other 2 cases. So it's okay that we're going to belabor this a bit because it'll really help. Is that I'm going to not worry about z for a second. I'm going to draw the line 2x plus 3y equals 6. And then I'm going to let it extend in the z direction. Right? So first, draw the line 2x plus 3y equals 6. Then extend it in the z direction. Now, if that's a bit confusing, that's okay. Right? We'll do it really basic steps right here. So first of all, we can even do this in 2 dimensions at first. Right? Like in the xy plane, the line 2x plus 3y equals 6, that has intercepts, right? When y equals 0, x is 3, and when x is 0, y is 2. So what we get is a line going through those 2. Let me actually do that in blue. Let me make those blue too. That is that line. If there were no z in sight, that would be it. So what we'll do next is I'm going to move this into 3D. So in other words, we go to XYZ space. And look at the way it works. We've got a 0.3 units in the x direction and a 0.2 units in the y direction. So we've got a point right here and a point right here. Those are the 2 points that we drew up on the picture above. And then we've got our line, which goes like this. So this guy that we just drew, this is 2x plus 3y equals 6 with z being 0. But now, here's the thing. But z could be anything. So what happens is, if you imagine this line extending up and down, and I'll do this in blue too, because it'll help, I think. But colors aren't mandatory, but it can really help with the showing you what's going on. So I take this line, and I'm going to be a bit sloppy with it. I'm not going to label too much right now. And we'll stretch it vertically, both up and down. And so now again, it's a plane. It goes up and down forever. It goes sort of left and forward forever and right and back forever. But what we did is we extended it up and down. And again, doesn't need to be perfect, right? If you like, you can draw a slightly better picture than this. Let me draw one where it just hits the axes. You could do, if you want it to be really fancy. And again, like I said, don't obsess too much about drawing perfection, right? But for some people, it can really help to have a really lovely picture. And if it does, that's great, right? This is where it hits at y equals 2. This is at x equals 3. There's like an axis hiding back there. There's the origin right in there. It goes up and down, left and right forever if you wanted to shade it in. I actually sort of recommend don't shading these things in because it can really obscure the pictures, but I'll do this one just as a sample. So again, if you look at this and it helps you wrap your head around what's going on, then great. But draw whatever you feel you need to draw to have it make sense. Doesn't matter, totally up to you. Right? So this is the case where we have 2x plus 3y equals 6. And so notice z is missing. So we ignored the z, drew it in the xy plane, and then extended in the z direction. So let me do an analogous example for the other two cases. Let me clear the screen off. So take a second to look at this one, run through it in your head. But basically I'm going to do the exact same thing. But first one I'm going to do is with the y missing, and then with the x missing. So let's do, for example, 2x plus 4y equals, say, 8. Oh, sorry, not 4y. I wanted to do 4z. So first, notice the y is missing. If I looked in the xz plane, and what's fun about this, you can do like a cursory drawing, right? You can go to the xz plane. What you can do is you can figure out where the intercepts would be. So the x-intercept, when z is 0, x is 4. When x is 0, z is 2. So you get this. And you can extend the line or not extend the line. Variety of approaches, draw whatever makes sense. Right? So that's in the xz plane. And then what I'm going to do is I'm going to move that into space. And so first thing I'm going to do is I'm going to say, well, look, this was at 2 right there. So along the x-axis, we were at 4. Along the z-axis, we were at 2. So the line we just drew is this line. And then what I'm going to do is extend that in the y direction. Because here, in this case, because y could be anything. Again, doesn't need to be perfect. If you want a lovely picture, if it helps, if it's helping, you could just draw part of it. You could draw the piece that's to the right, and you could say like, well, here's your z-axis, here's your x-axis. They come down. There's the origin right there. That extends out. We've got an intercept up at 2 and an intercept over at 4. And again, that's just a piece of it. It extends left and right forever. Whatever it takes to get a reasonable picture for you. Just practice, practice, practice. Share it with your friends. Give yourself feedback. And for the last one, I'll do with the x missing. Say y plus 3z equals something like 6. So now first ignore x, and we would look in the yz plane. So I'll draw the yz plane. What we'll do is we'll say like, okay, well, when y is 0, z is 2. And when z is 0, y is 6. That's that line. Then what we'll do is we'll move this into 3-dimensional space. So we'll draw this exact same thing first. So we'll say, okay, in the y direction I'm at 6. That's here. The z direction we're at 2. Connect those. That's the same line. And then this sort of slides forwards and backwards. It extends in the x direction, because x is anything. And again, if you want a fancy picture, that's fine, if it helps. We've got this thing, imagine it's at an angle. That's at 2 and at 6. And we've got our axes. This one comes out here. Then that comes up there. These meet. And this slips out. There's no intercept over there. It slips out in the x direction. So it's on a slight angle. Again, it goes back forever, forward forever, left and up forever, right and down forever, to give you the entire plane. So again, like I said, just practice these. They're pretty challenging to draw, and some of them can be tricky. There are some examples in the book which are awful, but don't worry too much about the difficult ones. Just work on the ones that make good sense. You know, take the ones that I've done here and just tweak the numbers a bit. Like what if this were, you know, 6y plus 3z equals 6, for example, or equals -6. Just give it your best shot, and you'll run into some that you struggle with, and that's fine. And you'll run into some that you don't struggle with, and that's great. So just have at it and try a bunch. So the last thing I want to do is I just want to do one more thing related to planes, and that has to do with distance from a point to a plane. We did a similar thing for distance from a point to a line. This is significantly easier, so I'll just give you a really simple formula. I won't derive it this time, and I'll just do a simple example just to do some practice. So let me clear this off and then just do that. So for distance point to a plane. So we'll say, here's the formula. If a plane has point P and normal vector n, and if another point Q is not on the plane, so again, we're measuring the shortest distance from Q to the plane is given by. So the one thing I would say be careful about. It's really easy to confuse the two distance formulas we have so far. In other words, the one from a point to a line and the one from a point to a plane. That's just practice. You just need to sort of look at them and remember. The way that I always remember is one is a dot product and one is a cross product, and the plane is the easier one, and the easier one is the dot product. So this turns out to be the absolute value of PQ dot n over the magnitude of n. So if you remember, the one for the line was the magnitude of PQ cross L over the magnitude of L. This is a bit different. So really simple example. Let's say find the distance between, say, and what I'm going to do is I'm going to give the plane in a, say, in like a form like this. 2x plus 3y plus 3 equals 10 between that plane and the point, say, 5, 2, 6. So what do we need? What do we know, right? We know the point that's not on the plane. That's our Q. Now, we need two things. We need P. P is a point on the plane. P is any point on the plane. What this means is it's any point satisfying that equation. satisfying that right there. So literally anything. So let's do, for example, P is 500. That satisfies that. All right, it's a really easy one. 2 times 5 is 10. Make Y and Z 0. You're good to go. You could do something else. You could do like 2, 2, 0. That would work as well. Lots of choices. Doesn't matter. The distance will be the same. The calculation will be different. The distance will be the same. And n, remember what we said before, that the coefficients of x and y and z, those came from the n. So 2i plus 3j plus 3k. Those are the coefficients of the plane. Right? So then we just do the formula. I need pq, that vector pq. I take q and I subtract p. So that's 5 minus 5, 0, 2 minus 0, 6 minus 0. So the distance, write down the formula. So absolute value. So take the dot product of PQ, there is our PQ, and there is our N. So we dot those. So remember how that works. That's 2 times 0. Let me actually write this out officially. That's 0 times 2 plus 2 times 3 plus 6 times 3, absolute value. Now, for what it's worth, we didn't derive this formula, so you shouldn't necessarily look at it and say to yourself, oh, it's screamingly obvious, right? The one for the line, we figured out where it came from. This one, I'm just handing it to you. And then the magnitude of n is the square root of 2 squared plus 3 squared plus 3 squared. This simplifies a little bit, not overly necessary. At the top we've got 6 plus 18, 24, and we've got the square root of 18 plus 4, which is 22. And that's the final answer. So again, just another useful formula. It's good for practicing magnitudes, dot products, etc. It's good for working with equations of planes and pulling out information that we need. So that is the end of 11.6.